I guess it's time to start with our next speaker, Dr. Mark Raymer from Michigan State University. Just kind of give a quick background. I think I know Mark for almost 6 years or so, or a bit more than that. Yeah, I guess more than that. So
I don't remember when.
Yeah, well, I mean, apparently there was a poster with my name at SFN that I couldn't go because I didn't have a U.S. visa. My colleague was presenting, and Mark came to the poster and gave him quite a lot of advice in terms of how to do data analysis. So that's how we start, basically.
That's how we met.
Exactly.
Virtually.
And then Mark came to UBC. We did very good collaboration, and we are continuing to collaborate. So it's my pleasure to introduce Mark, and I would be happy to.
Thank you.
Looking forward for your talk.
Thank you, Majid. So actually, I saw Majid's poster as I was in a rush going from one part of the poster hall to another part of the poster hall, and hadn't expected. And then these beautiful brain images, and I saw the brain in action. This is what we want. So that's how we got together. Okay, so I'm going to be talking to you about multivariate techniques for neural data analysis. So I want to ask, how many of you have taken or studied any kind of multivariate techniques, usually PCA, in some sort of statistics course? So that's half, roughly. Okay, thank you. How many of you have used PCA on neural data, neural activity data? So about the same number. Actually, even more. Huh, okay. This course is for you. All right, how many of you have used any other multivariate method, like ICA, factor analysis, NMF, et cetera, et cetera? Okay, good. Okay, a few. Great. Well, I know you have, Don. Okay. So, all right. So then this, I'm going to try to cover both those of you who have some experience and those of you who are brand new. This will be roughly, whoops. Nothing's the right rough outline. Where are we here? Majid, what do I press to get this? In lectern HDMI 1?
2. I think you're in 2.
2. All right, now we're back. Good, thank you. All right, so this is roughly what I'm going to cover, and we'll pause to 2 points for some coding. So let's start with the question, when and why would you use multivariate techniques? So I'm just going to mention a couple of nice examples that have appeared recently. So this figure is from a paper in Nature a few years ago, and what they're doing is recording from hundreds of neurons in prefrontal cortex, and while a monkey is doing a choice task, and he has to sort of interprets the moving dots task with a color variant, and he's got to sort of determine which condition he's in and then figure out what's actually happening to those dots or which colors are more dominant, and then make a choice. So what they were able to show is that most of the interesting variation relevant to the choice the animal's making or how he's perceiving the stimulus can be represented in 3 dimensions, and actually it turns out that you can represent almost everything you want in about 7 dimensions. So that's much less than the 200 dimensions that they had to start with, the 200 variables they had to start with. So they constructed these variables, and they were able to show that the trajectories under various conditions followed pretty stereotyped, nice pathways, which are shown by these sort of linked dots here, where you're connecting the dots starting from when they presented the stimulus to the animal to when the stimulus went off. And you can see there's sort of a nice, depending on various conditions, these different colors represent slight variations of the condition. You can see that there's fairly similar kinds of development of activity, at least along these 2 dimensions here, and then another 2 dimensions over here for when they have to make a choice by another aspect. So why would you want to do this? Well, what they then went ahead and did is they took the 3 leading models, which had been in the literature for 20 years, about this task, and everyone thought they knew how this task was being done, and they went and simulated neural networks according to the various models, and then they did exactly the same analysis. So remember, here's what they came up with. This is a sort of stylized version of what they found on their data, and here are the results that they obtained from doing the same analysis using 3 different models of how this choice task was done. So what do you notice? Which model is right? Which model fits the data? Yes? You want to answer that? Anyone want to answer? This is not a trick question. This is the state of neuroscience today. None of the above is the correct answer. None of the above fit these data at all well, which means you have to go back to the drawing board and come up with a new explanation. I think that's what makes this the most exciting time in neuroscience, because we have the opportunity now to falsify a lot of ideas that have grown roots, as it were, in the cognitive science community. So that's a particularly good example. They used a variation of PCA. Here's another example from a paper published last year. I think this is in Cell, wasn't it? Not Nature, but a pretty nice example. Here they're using PCA to organize stimuli. So one of the things we're very interested in is how primates, like ourselves, recognize complex features like human faces. But how would you possibly discover what the relevant variables are? I mean, there are an infinite variety of faces. How would you find out which features are being responded to? And what Doris Tsao did was to segregate the shape from the sort of appearance of the faces, and then do principal components analysis on sort of the dot map of the shape and the texture map of the appearance. And then she found that this almost infinite variety of faces could be pretty well represented in about 50 dimensions is what she used, but actually most of the information was in about 10 dimensions. So that's enabled her to really elucidate how primates recognize faces. So roughly speaking, whenever you're recording neural activity across many cells or many brain regions, then you want to use some sort of dimension reduction algorithm, and that will help you understand the dynamics, the intrinsic dynamics of the circuits you're recording. So the key here is this shift from averages across many trials to single trial analysis. We want to understand what's going on every time the brain is engaged with a task, not just what's happening on average. And it's going to turn out to be important because, as many of you have noticed, you can never get the same recording twice, right? You put the animal through exactly the same circumstances 100 times, you will never get exactly the same pattern of brain activity. And what we're trying to do is understand why is there variation. Okay, so I want to switch to sort of basic concepts now. And what are our goals? There's a little more text on these slides than I would like, but that's partly because some of you are going to be using them for reference. So roughly speaking, we want to create new variables. We're not selecting variables. We want to create synthetic variables that summarize as much as possible of the information in our complex, rich data set. And we want to be able to select those so that we can reconstruct most of the relevant aspects of our data from these summaries or abstractions. Roughly speaking, we divide into linear and nonlinear methods, which is basically like saying elephants and everything else. There's a lot of linear methods, and they all create new summary variables out of linear combinations of the variables you measure, and that's equivalent to finding new axes in a high-dimensional state space. So if we think about this in terms of the data matrix, so if you represent the variables in the columns, so this could be your neurons or your voxels in an fMRI or your pixels in an optical imaging recording, then what we aim to do is to represent a big time series. So the vertical axis here is time. We want to represent a time series of many variables, so big matrix, in terms of two much smaller matrices. One is going to represent the sort of time, the dynamics of the processes, and the other is going to represent how do you get to the processes or the underlying factors from the measures you've made, and vice versa, and back again. So we say this is not exact, this will be approximate, but we hope that this residual matrix is of errors, E, is relatively small. So the way I've oriented this, which is the common statistical convention, the variables are in columns, the instances or the time samples are in rows. You may also see this, inverted engineers particularly like to represent data as a whole lot of vectors, so then the variables would be in rows and the instances or time samples would be in columns. All right, so I'm going to start with, and the only one we're going to have time to spend time on is the sort of workhorse, which is principal components analysis. And this is basically rooted in classical statistical theory. It dates back to the 1920s. And the idea is that what you want to do is take all of your measurements and try to plot them, if you can imagine, in a high-dimensional space. So if you have 2 dimensions, you can plot them on a piece of paper. If you have 3 dimensions, you can imagine them in 3 dimensions. But you can, by an effort of imagination, imagine if you have 10 variables that it's a sort of point cloud in a 10-dimensional space. But 10-dimensional spaces have a geometry as well. And what you're looking for are the long axes of the ellipse of point clouds. And you might ask, well, what if it's not an ellipse? Well, hold that thought. That's a good thought. We'll get to that in a minute. So just for now, suppose that your data is an ellipse in a high-dimensional space, and what principal components analysis is doing is trying to find the axes. So it's trying to line up the new axes of the new summary variables with the long axes of the data cloud. And that's going to mean that you're going to get most of the variation along these axes. So to think about it in terms of data, what you're doing is you're finding, if you here you have 2 variables, x1 and x2, we're going to find the combination of x1 and x2 that has the most information about both of them. And that really would be the sum of x1 and x2 because they're positively correlated. Not strongly, but they are positively correlated. So if you were to take any one number that would have the most information about both of these data numbers, that number would be their sum or their average. And by convention, we take coefficients whose sum of squares is equal to 1. That's an old convention. And it's used in all the software, but you'll notice that other methods don't follow that convention. Basically, only principal components analysis does. So if you compare your coefficients from principal components to coefficients from factor analysis or from ICA, they won't be on the same scale. But what we're doing is basically picking new axes so that these same data points here are going to sort of, you can see now that the first axis summarizes most of the information about things. We can get an additional bit of information by this orthogonal axis at 90 degrees. Okay, so why do we use PCA? And I recommend, I use a lot of fancy techniques. You'll use lots of fancy techniques. There are more fancy techniques being invented all the time. But PCA is a good workhorse because we have a good mathematical theory that tells us how close we are to the answers. So we can estimate what the error in our principal components, in fact, is, and get some confidence in what's real. Another advantage of principal components compared to nearly any other technique, and especially to some of the fancier techniques, is if you run it twice on the same data set, you get the same answers. That's really nice when you have to, you see something wonderful and you take it to your boss and you press the buttons again and you get something completely different. That's never happened to you, right? Okay, so reproducibility is really desirable. So those are some advantages. So it's always a good thing to try at least once. Some weaknesses is that you can't get all the factors. You can't, you may have some summary variables that are meaningful, but if their variance is too small, if their variation along that axis is too small, you can't get good estimates of that direction, of that summary variable. Another drawback is that if you have, as you often do, highly skewed measures, so for example, you've got lots of small ones, a few medium-sized ones, and a couple really enormous ones that are real, not just errors in the data, PCA is much distorted, over-influenced by those outliers. And so you will get really strange-looking principal components. And we'll talk about what to do about that in a minute. The final problem, or not the only final problem, but one other problem is that it's often hard to interpret the results of PCA. And we'll talk about some alternatives that might be easier to interpret. Okay, so what's the first question about that is how many principal components to use. So principal components analysis will give you as many axes as dimensions you put in. But you always select the first few. And how many do you select? Well, the sort of tool of the trade is what's called a scree plot. How many of you do mountain climbing? So you know what scree is? So all those boulders that are forming this kind of pile on the side of a cliff. And what we're looking for, what these represent, are the lengths of the data along the different axes. How much variation are you getting by representing the data on the first axis, then on the second axis, then on the third axis? So if we go back to this picture here, we're asking sort of how long are these different axes? So the first principal component is the one with the longest axis, and that's typically quite well. It varies. That's typically a real principal component, and it's estimated well. Our theory tells us how well it's estimated. The rule of thumb is that you can estimate well a component if the variance is well separated from those on either side. So that's the key rule of thumb for interpreting these plots, is that there may be more components down here. These axes may reflect real things, but you can't possibly disentangle them. They are all mixed up with the noise. So the ones you can probably disentangle are the ones that really stand out from everything else. And those are the ones you should focus on. So in this case, 3, maybe 4 are reasonably well separated. There may be more, there may be other real components, but we can't get them by PCA. Okay, any questions so far? Any arguments? Okay, then I'm going to suggest we go to the exercise now. So I think it was sent out as an addendum yesterday. So there's a Google Drive folder. Let me just... so if you have Google Drive open, it should be here. And okay. It's also in the Dropbox, yeah. But if you downloaded it yesterday, if you downloaded it yesterday early, you may not have gotten the sample code, so go back there and get the sample code, and it's also on the Dropbox. Okay. All right, then let's go ahead. Now, would you like to work through it a little bit yourselves first, and then I'll do it as a demo? So why don't you take 5 minutes, work through as much as you can, and then let's discuss it.
Yeah, there is where the lunch is.
Some of you have plowed ahead right to the end. So let's just discuss. All right, so let's start with loading things. This is meant to represent the kind of data you might get if you're recording from, let's say, 20 neurons, a nice round number, you're aggregating spike counts in 100 millisecond bins. So let's do the usual thing that we do, which is to look at the mean response. Oops, let me close all again. Okay, so you see something that looks like this, right? So far, so good. So what would you interpret this to mean? So let's say you've done your recordings, you're talking to your boss, and you're saying, what does this mean? So you've done 30 trials, this is the average activation. So you can see, anyone want to interpret this for me? Well, you can see that there's at least one group of neurons that activates pretty late, maybe after 300 milliseconds. There are other neurons that seem to activate early and then seem to deactivate. So that's nice. It's a nice sort of information processing story. And if you were to look a little deeper, you'd say, well, it looks like some of them activate a lot and some activate less, right? And we don't know why some are less. Maybe they're just not connected in well enough or something. We could make up a story. We can make up a story for just about any data set. But let's look a little further then. So let me get this. So what I'm going to do to first construct this, set this up for multivariate analysis, is to do to concatenate all the trials. So instead of three-dimensional array, I'm going to make this into a two-dimensional array, and there's a fancier way to do this with perm, but I won't Okay, now let's do principal components analysis. So the principal component command in MATLAB is Pca, and it returns up to, I think, five outputs. The ones that we're typically most interested in are the first three. So the loadings are going to tell you what combinations of variables are included in each of the summary variables, or what combination of measures are included in the summary variables. The scores sort of tell you how these summary variables change over time. So that's your clue into the dynamics of the system. And the variances, or vars, tell you how long these axes are. So let's do this. Oops. So here we have, what would you say? So how many of these principal components can we really be confident of? One, maybe two if we really have a lot of faith. So yeah, one. Okay, so what do those principal components look like? So let's take a look at how they're loaded. And that should give us this. Okay, so what can you see right away with this plot? So this is an unusually, or unrealistically clean example where the loadings are nicely separated into positive, oops, did I mess that up? No. Positive and negative loadings here. So we've got one group of neurons that are all pretty much equally weighted in the summary of the first variable, and another group that are all weighted oppositely. So what do you think that corresponds to? Well, we can look at what the loadings are. So what do you see? So the first group are loaded negatively, the second group are loaded positively, and they'll turn out to be those that respond early and those that respond late. So that makes some good sense. Now, although I've told you that you should not trust the loadings from or be confident of the numbers in the loadings for components where you can't separate the variances, there's often useful information there, so it's worth looking. So I am going to first plot an image. Actually, I'll do the plot first. No, plot 3. Plot in 3 dimensions. And if we look at this now, which should be a nice 3-dimensional plot, and rotate it around, what can you see? So it looks like there are really maybe 3 clusters of neurons, a cluster here, a cluster here, and a cluster here. So that are not equivalently loaded, but are fairly similarly loaded. So it's looking like, there should be really 3 factors here, even though we can't tell them apart with Pca. So one thing we might look at is, what are the images of the loadings, and we'll keep this for comparison later. So you can see that looks like principal component 1, which corresponds to a group of about 10 neurons. Principal component 2 corresponds to maybe, looks like 3. And then principal component 3 looks like has some of the same alternation pattern, but looks like a bit of a mess. It's going to be really hard to make any sense of that. But let's just take a look at some plots here of the scores. So you can see that the principal component 1, which is in blue here, so the black bars tell you when the trials begin and end. So it looks like every time that there's a stimulus presented at the black bar, we're getting some activity on principal components 2 and 3, but it's pretty hard to interpret. And we're getting then later, about 200 milliseconds later, some activity on principal component 1, which is therefore the sort of late responding group of neurons. And this sort of illustrates both the strength and the limitations of principal component analysis. The strengths are we could see that there were probably 3 groups there. The limitations are that it's very difficult to interpret what the dynamics mean. We can sort of see that there's something happening early, but we don't know what it is. And it's only the late responding neurons that have a nice clear trace. So let's come back to that then. I want to switch back to the show. Okay, oops. Here we are. So, where are we? Am I on the right? Am I on the right slideshow here? Sorry. No, I'm in the wrong slideshow. Sorry. There we are. Okay, so I want to discuss some practical issues and some caveats here. So first, the numbers you're getting are not sort of ideal true values. If you were to record another set of data from the same neurons under the same conditions and do PCA, you would hopefully get similar but not identical results. The theory tells you that these numbers are estimates of some true summary variables, but you would need an infinite amount of data to actually compute those true summary variables, which we don't have. But the nice thing is that the theory tells you how far apart they are, and it basically scales as the reciprocal of the square root of the number of time samples you have. So the longer you record, if you record for 4 times as long, you'll get half the error, or twice as precise. Okay. One other thing that you will want to be aware of is that in many neural data sets, you do have extreme outliers. So you are going to, if you leave those in, they will distort the principal components quite substantially because the algorithm is always trying to capture the biggest fluctuations. But you don't want to take them out because they are real data. They're not, assuming that they're real data, they're not an error. So what do? A good rule of thumb is to scale them back. You keep them as very large, but you don't make them 10 times as big as any other fluctuation, which they might be. You bring them down to, typically a rule of thumb is about 2.5 or 3 standard deviations away from the mean. That's about as large as anything can be and still be consistent with being a normal distribution, which is the kind of or Gaussian distribution, which is the kind of distribution that principal components works best for. Another thing to keep in mind is that if you have a variable that has more fluctuations than another variable, and you put in those raw measures, principal components analysis will automatically look to explain more of the variable that is varying the most. That may be what you want. It usually isn't. If it's not what you want, then you need to rescale the variables so that they are more or less on the same playing field One of the things that most people do is do a z-score transform. So just take in Canada you say z-score, don't you? I'm Canadian. I've been brainwashed. So a z-score transform. So you basically look at subtract the mean, divide by the standard deviation. And that's what I've illustrated here. I find, and some of the other data analysts I talk to find, a more robust procedure is because there's often a level of irreducible noise in your data, a more robust procedure is to sort of try to identify some scale at which you think the fluctuations are meaningful, and then scale everything above that down to that scale, but leave the small ones, because they're often reflecting just noise. And it often happens in many of our optical imaging data sets. We may have thousands of neurons, but only 100 or a couple of hundred of them are actually doing most of the work. So we don't want our principal components to reflect all of the sort of borderline fluctuations, which are often artifact in our calcium imaging data. So I find that this procedure typically works much better for optical data. Okay, so what about some alternatives to PCA? Some of you have been using those. So remember, the rule of thumb is you can get more information out of some of these alternatives, but they are more powerful tools. They are liable to do more damage, meaning that they'll give you results that you don't know how to interpret or that you will interpret in the wrong way. It's very common. It's very rare that I see someone making an egregious mistake using PCA, but it's very common that I see someone making an egregious mistake using some of these other methods, because they're just, they have a program, it gives them an answer, they report it in a paper, and they have no idea what are the conditions under which this answer is meaningful. And that's in the small print. Who reads the small print on the manual? You're just trying to get a result. So I'm going to talk about two of them, non-negative matrix factorization, which we'll do a short example of, and ICA. So the basic idea of non-negative matrix factorization is that if you have additive processes, let's say, for example, you might suppose that you have in a region you're recording from, you may have a number of different clusters of pyramidal cells or excitatory cells that respond to different kinds of features. And they may interfere with each other relatively little, but some cells may participate in several clusters. So it's possible for a cell to respond to more than one feature or more than one aspect of a stimulus, but it's unlikely that they respond evenly to all of them. So we've had a lot of papers in the last 5 years on this mixed cell activity, where a cell responds to several but not all aspects of a situation. So you want to be able to disentangle that, but the thing is, they're all positive, they're all excitatory cells, so they're all sort of responding the same direction. It's hard to understand what a negative coefficient could mean. So you want to decompose these into all positive coefficients, and that's what non-negative matrix factorization does, is it restricts the set of, so instead of finding the S and the A that most closely approximate X, whose product most closely equals X, we pick an S and an A which are both positive, whose product closely approximates X. But the drawback then, as you might guess, is that with the restriction that these be positive or zero, or at least non-negative, that very much limits us in how closely we can get to our original data matrix. So we usually cannot summarize as much information with non-negative methods as we can with, say, PCA or factor analysis. But on the other hand, the results we do get are usually much more interpretable. The other thing to watch out for, or two other things to watch out for, is that this is one of those things where you run the algorithm again, you'll get different answers. And you have to spend a lot of time running it, seeing how consistent the factors that you get are in order to be confident that they're real. The second issue is that most NMF algorithms require you, the user, to specify how many factors you're looking for. PCA will give you everything, and then you figure out which ones you want to keep. NMF, you have to decide ahead of time how many you want, and it will try to find the best decomposition with that many columns and that many rows. So that places a lot of burden on you. How do you know how many factors there are? Very good question. Well, we actually use this instability feature in a sense to our advantage to answer this question. So what we typically do is we run the NMF algorithm, again, 10 or 20 or 100 times with 4 factors or 5 factors or 6 factors, and we look at how consistent those runs are. If we look at 4 factors, we're typically, may see that, well, we're getting a lot of jumble. We're getting things that don't really correlate very well. Can I draw on the board here? So if we were, can you see this or not? All right, so supposing we do this with 4, 5, and 6 factors, what we often find is that the sort of the stability, meaning how correlated are the scores that you get from one run to the next, maybe relatively low here, maybe higher here, and low again here. And that gives us an indication that maybe 5 is the best number to use. And there's some theory that tells you that if the NMF model is satisfied, that's a good way to actually figure it out. So that's a good rule of thumb for using NMF. I think we have time for the exercise. So if we go back, it'll take 2 minutes. So again, using the same data, what I'm going to do is reconstruct I'm going to decide that there are 3 factors, and I'm not going to go through the whole justification of that, but let's take a look at those. Okay. So now you can see something that was, when you look at, if you go back and look at the PCA, it'll make more sense, but now you can see, okay, now this group of 10 neurons is really clearly one cluster. And this group of 10 neurons factorizes pretty nicely into 2 groups of 5 each. Okay, nice, neat pattern. All right, so we have so these 2 groups and this group and this group are really responding quite differently. So let's take a look at what they might look like. So let's get just a subset of these. All right, so here again is our blue factor is factor 1. That's the one that's the late rising factor. And now I think you can see that sometimes you get a really strong component from factor 2, and which is in red, and sometimes you get a really strong component from factor 3, which is in yellow. And sometimes you get both. So it looks like what we're seeing is that both groups of cells are responding to the stimulus, but they're alternates. So this is an idealized data set, but this is features that I see in many real data sets, that you don't necessarily get the stereotype response. You often get different groups, different clusters of neurons, which are not necessarily highly correlated themselves. You may even get negative correlations between them. And you notice that you can certainly interpret this much more easily because all of the loadings are positive. Any questions or arguments about that? Okay, well then we'll go back to the show. All right, so the other very popular technique is independent components analysis. Let's put that. Oops. So the idea of independent components analysis is to directly address the problem that I mentioned earlier, that the principal components approach assumes that your underlying factors are close to Gaussian in distribution. That is, most of the values are around their mean value. You've got a very small number of extremes on either direction. But often neuroscience data isn't very Gaussian, and often the underlying factors may not be Gaussian. So the idea is that for ICA is that you are looking for the most, so it's called independent components because you're looking for those combinations that are are closest to being truly independent. That is, they give no information about each other. The drawback to ICA is that if you do have normal data, you will get an answer out of ICA, or out of many ICA algorithms, but it will be complete nonsense. It doesn't, it's not able to segregate those very well. So let me just give an example. So here we're supposing that we have two, so let's say, sources of stimulation to two group of neurons. So let's say we have source 1 on the x-axis, source 2 on the y-axis, and what we are going to do is we're going to construct this data set. So neuron 1 is going to respond 2/3 to source 1 and 1/3 to source 2, and neuron 2 is going to respond 1/3 to source 1 and 2/3 to source 2. So you can imagine this being different tunings or similar features of a situation. Okay, so this is not real data. This is what we're attempting to reconstruct. That would be the truth, and this would be what we observe. So if we're measuring neural responses of neuron 1 and neuron 2, then, at this sample, for this trial, we observed this response of neuron 1 and this response of neuron 2. And sometimes both are responding and sometimes both are not responding. Okay, so that's the kind of data we're dealing with. So let's look at what happens. Supposing we do principal components analysis. So what principal components analysis is going to do is say, okay, well, this is sort of an ellipse here. Let's find the long axis of this ellipse. And where's the long axis? Well, it's where it usually is. And so then let's put this on its long axis and say this is the first component and this is the second component. And that's a kind of dimension reduction. Yes, the two are correlated, but it doesn't really help you recover the original sources or the original loadings on these two neurons. So you would have essentially one component that explains most of the variance, but it's basically the average of the two of them. It doesn't help you understand what's different about these two features of the stimuli. So what ICA does is it starts where PCA leaves off, says, okay, what we're going to do is first, we're not interested in the scale. We don't care, we throw away the scale information. So we're going to squash this long axis until it's the same scale as the shorter axis, and if you have it in higher dimensions, it basically means making all the axes the same length. And that makes the correlation 0. So you couldn't do anything with principal components analysis, but you notice something that these variables, even though they're uncorrelated, are mutually informative. That is, if we know that the variable 1 is less than 0, we know that variable 2 is very close to 0. If we know that variable 1 is positive, then we know that variable 2 is typically quite far from 0. So they're not independent. That is, one gives you some information about the other, even though they're not correlated. And this is, I think, I can see a lot of you scratching your heads or sort of looking, how is this possible? Because I was told that, if things are dependent, they're correlated. Well, that's true for Gaussian or normal random variables, but not true for highly skewed or other pathological, what we used to call pathological, but actually are fairly normal kinds, or fairly typical, I should say, kinds of variables, not normal. All right, so what ICA does is it says, well, let's try rotating this around until we get to the point where these variables have the least information about each other. So we can imagine trying a variety of rotations, but once we get back here, they are truly independent. The one feature of the, if you've done your experiment so that the two main features of the stimulus are statistically independent, then your neural response, which reflects both of those features, will show up as statistically independent as well. So the idea is that we can reconstruct which aspects of these features the two neurons are responding to, even though they're both additively responding. Now, I like ICA, I use it, but you should be very cautious. So again, you should make sure after you've done your ICA, you should look at the distribution of your scores. And if they look Gaussian, you've probably got nonsense. There have been a number of papers published, especially in the fMRI literature, using ICA, where it's very trendy, and getting some very strange results, meaning all of their factors have Gaussian distribution. So I don't really believe any of those papers. Again, this is a method that is sort of iterative. If you run ICA in the same data set several times, you may get several different factors and in a different order. So as a sanity check, run, again, like NMF, run it several times and keep those factors that appear, meaning that you can find something that's at least 95% correlated in all the runs. And
Are you using the word normal and Gaussian?
normal with a capital N, yeah.
So if you have normal distributed variables,
If your underlying factors are normally distributed. The ICA model is supposed to work for any distribution of your measures, which may often be close to Gaussian. But if the underlying factors are also Gaussian, then it can't find them, because once you reduce the correlations to zero by principal components, there's nothing to go on.
So it basically takes out what we're used to interpreting non-correlations.
Yeah.
Takes that out first.
Takes that out first. So it removes the structure that we would see through correlations, which is entirely what PCA focuses on. So it ignores that and looks at the sort of amount of mutual information between two potential candidate summary variables, and looks for those that are the most independent, the most uninformative about each other.
Is this a fact that not a lot of people are aware of, or is this common?
Well, let's put it this way. This is a fact that all of the experts know, and very few practitioners know. So yes, it's a fact that is not widely enough known. Okay, so any questions or comments from anyone else?
I'd like to know if anybody knew that. Okay.
4.
Not that obscure. 2%.
4 people knew. Good.
Now I know.
Spread the word. Okay, some perspective. So I've talked about 3 methods, and that's by no means exhaustive. These happen to be the 3 most popular methods in neuroscience, but they are by no means the only methods available. So this is more for your reference later, but I'm going to first summarize a group that I'm calling blind dimension reduction algorithms, meaning that all you're using is the neural activity data itself. And so we've talked about many of the linear approaches. There are also a number of nonlinear approaches, which I'm not going to go into, but then the variables don't correspond to sort of axes. They correspond to some some different combinations, and you can often visualize your data as sort of a curved surface in a high-dimensional space. That's what the goal of a lot of these methods is. But those, what I call blind methods, are not the only approaches. We have also a number of sort of informed approaches. So if you are also, say, measuring behavior at the same time, you may want to select your dimensions that are most informative about behavior, as well as being, the best approximation to your neural activity. You may decide you want to ignore dimensions that have nothing to do with the behavior you're interested in. That's the approach that was taken by the Monte paper that I showed you some figures from at the beginning. And Christian Machens, Mark Churchill, and Jonathan Pillow, a number of other people have taken similar approaches where you're using information about the behavior to sort of select some dimensions rather than others. There are also a whole lot of methods that are intended for time series. So I'd like to point out that most of the dimension reduction methods were originally designed for data other than neuroscience data, often for data that isn't even time series data, but is, let's say, sociology or some kind of engineering measurements. There are a few dedicated methods for time series. They have not found a lot of use among the neuroscience community, with some exceptions. I think partly because they're hard to use, and partly because they don't seem to give any really striking advantages, at least haven't so far. So I'm not necessarily recommending these. But there are also a number of researchers working right now on trying to develop better methods for dynamic time series that are specifically aimed at neuroscience data. So far, they're pretty complex. I don't know if any of you heard David Cicillo talk about LFADs. That's probably the sexiest method out there right now. It's a recurrent neural network that's an abstract way used to simulate the dynamics of the measures you're recording, and it is able to do quite well at representing. So it's a kind of dimension reduction approach that is deliberately designed to sort of mimic the kinds of dynamics you might expect. He's not trying to reconstruct the neural network you're actually recording from. That's impossible. We don't know the connections, and of course there's many inputs to the region you're recording from that we can't observe. But LFADS tries to abstractly estimate what kind of neural network might produce the kinds of observations you're seeing, at least in an abstract way, and is quite successful at that. That paper will appear in Nature Methods quite soon. Okay, so I think that's it. I think I'm almost exactly on time. So thank you for your attention.